Introducing qaTT, your AI-powered copilot designed specifically for SRE and DevOps professionals. Seamlessly integrated with a range of incident management, notification, ticketing, monitoring systems, and messaging platforms, qaTT transforms your workflow by offering adaptive, step-by-step solutions in an easy-to-understand and explainable style. qaTT is designed to function within 3 specific environments, each tailored to different security requirements. First, deployment exclusively with the client's proprietary playbook knowledge bases. Second, hybrid integration combining the client's internal playbook knowledge bases with the advanced capabilities of large language models. Third, a fully autonomous AI-driven solution that operates without pre-existing playbooks. Let's look at how qaTT helps to resolve incidents. As usual, the incident resolution process starts with receiving an incident message in a dedicated Slack channel. In this case, it is a Zendesk ticket describing the problem. As we can see, this is a fairly broad description indicating the error. Let's see how qaTT solves this problem in a step-by-step manner. Since the incident message includes no details other than the website's URL, qaTT will first check the URL name by examining the DNS records for demo.qaTT.online. After obtaining the DNS records, qaTT analyzes them and, upon confirming that the DNS name is correct, proceeds to the next step in diagnosing the issue. qaTT pings the IP addresses identified in the previous step. After ensuring the IP addresses are responsive, qaTT queries the knowledge graph, as previously mentioned, to access data about the infrastructure, specifically the collection of Kubernetes objects and their interrelations. This step is crucial as it provides qaTT's multi-agent core with the necessary context. Focus on Step 4. Based on the acquired data, qaTT recognizes that the website is deployed within a Kubernetes cluster and decides to begin diagnostics with the service object. In this context, qaTT utilizes well-known Kubernetes commands and displays their results, which facilitates tracing the reasoning process and manually reproducing the outcomes. Focus on Step 5. The service diagnostics reveal nothing unusual. Therefore, the next step involves qaTT requesting detailed information about the corresponding pod. Focus on Step 6. Based on the gathered information, qaTT determines that even though the pod is currently running, its last state was terminated due to insufficient memory. qaTT suggests increasing the allocated memory limit and prompts the user to input a new value. Focus on the input field. Let's assume the new value is 500 megabytes. Focus on Step 7. qaTT updates the relevant value, and upon receiving a positive response from the Kubernetes API, focus on Step 8. It attempts to verify the state of the pod. However, the Kubernetes API returns an error, which makes sense, as changing memory limits leads Kubernetes to delete the old pod and create a new one with the updated values. Focus on Step 9. Understanding this mechanism, qaTT queries the pod's state based on labels rather than the pod's name. After obtaining the command results, which include the pod's name, focus on Step 10. qaTT retrieves the previously unsuccessful command using the new pod name. Focus on Step 11. Having confirmed that everything is functioning correctly, qaTT concludes the step-by-step solution.